Hello, welcome to lesson 24 on the central limit theorem. We have n independent random variables, each with the same distribution. They have the same mean, the same variance, same shape distribution. Mean is mu, variance is sigma squared. And then we look at the sum. Let's call it t for total, x1 plus x2 plus dot 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 up to xn. This sum will be approximately normal. The mean will be n times mu. Variance will be n times sigma squared for n large. As n gets very large, this approaches a normal distribution shape. Mean n times mu, variance n times sigma squared. We are not told that each variable is normal, so we don't know. May or may not be normal, but the sum will approach the shape of a normal distribution as n gets large. Not going to do a full-on proof here, but just a brief explanation of the mean and variance. Expected value is additive, so the expected value of the sum is the sum of the expected values. Each of those is mu, so the total is n copies. Total of n copies is n times mu. Variance is additive when the variables are independent, which we're told, so it's the sum of the variances, which is sigma squared repeatedly added to itself, which is n times sigma squared. So for the sum, the expected value is n times mu, variance n times sigma squared. So an example of that portion of it, we have 40 independent, identically distributed random variables. Again, we don't know the shape of the distribution, but they're all the same. They're independent. We know the mean is 11, standard deviation is 3. Find the mean and standard deviation of the sum. So the mean of the sum is n times mu, 40 times 11, 440. Now the standard deviation is a little trickier. Technically, you have to square that 3, get 9, then use our formula here and get 40 times 9 for the variance, and then take the square root. Now the square root and the square cancel out, so shortcut formula for standard deviation is sigma times root n. So it's 3 standard deviation times root n root 40. So the standard deviation is 3 times root 40. All right, number 2. This is a full-on example. A charity receives 2,025 contributions. So that's the number of contributions. That's not the year. And they're assumed to be independent, identically distributed with a mean of $3,125, standard deviation of $250. Calculate the approximate 90th percentile for the distribution of the total. So we'll let T be the sum of those 2,025 independent, identical random variables. The expected value of the sum is n times the mean. So it's 2,025 times 3,125. The standard deviation is sigma times root n. So that's 250 times the root of 2,025, which is 11,250. This is going to be approximately normally distributed. As n is large, the sum approaches a normal shape. Now we're trying to find the cutoff for the 90th percentile. So we're going to use the z-score chart to find that threshold. The 90th percentile cuts off 90 on the left, 10 on the right. So we're going to look to the z-score, z-chart here. We want the area to be 0.90. So we go in the body of the chart for the closest thing to 0.90. We have an 8997 and a 9015. So 8997 is a little closer, and that's coming off of so 8997 is the closest one. That's coming from row 1.2. and from column 08, so 128 is the approximate z-score here. And then we have to convert back to a raw score here. So z-score formula, it's the raw score, in this case the total, minus the mean of the total divided by the standard deviation of the total. Cross multiplying, z times sigma is equal to x minus mu. This should be t, sorry, the variable here is the total. And so the total is equal to z times sigma plus the mean. The z-score here is 128. Sigma is 11,250. The mean was 2,025 times 3125, which is this 6 million number, 328,125. Combining here, we get a 90th percentile value of $6,342,525. So what we're saying here is that 90%, if you run this experiment many times, 90% of the time, the total is going to be underneath this value, 6.3 million. All right, next example. This is from the textbook, page 413, 8.14. A certain component is critical to the operation of an electrical system and must be replaced immediately upon failure. The mean lifetime of this type of component is 100 hours. Standard deviation is 30. How many of these components must be in stock so that the probability the system is in continual operation for the next 2,000 hours is at least 0.95. So assuming independence here, we have the setup here for the central limit theorem. Independent, identically distributed random variables. All right, so we're going to let x sub I represent the lifetime of a single component, the ith component. And then t is going to be the total. And we want continual operation for 2,000 hours. The expected value is n times the mean, which is 100n. And the variance is n times the variance, which is n times 30 squared, or 900n. Standard deviation is the square root of that, which is 30 root n. Now we want to find n such that the probability that t is greater than or equal to 2,000 is at least 0.95. So we want 95% on the right and only 5% on the left. So it's a little bit tricky here, but we want to guarantee that we're going to have at least a 95% chance that the system will run for 2,000 hours. So that we want that on the lower end here. We want only a small probability of the total being under 2,000. So we want the left-hand side of the normal distribution. We want 95% of the probability to be on the right and only 5% on the left. So we're looking in the body of the table for 0.05. So we're going to be in the negative portion here. We're going to look for 0.05. And it's really close here. We have a 0.0505. We have a 0.04947. It's really close to negative 164. Sorry, let me just make this a little bit smaller so we can see everything on the same screen. Okay, sorry about that. All right, so again, we have here right between negative 164, negative 165. So either one would be okay. Maybe to be safer here, we want to choose the negative 1.64 to make sure that we're past the threshold, but either one is okay. Negative 164 is the cutoff here. And that will cut off 5 on the left, 95 on the right. All right, so now we're going to convert this over to a raw score. So we want the total to be at least 2,000. The mean was n times mu, 100n. Standard deviation for the total is sigma times root n, 30 root n. And the cutoff is the negative 164 to get that 95%, 5 on the left, 95 on the right. So you cross multiply, 30 times negative 164 is negative 49.2. You could do trial and error here to find the first n that works. If you want to solve it algebraically, you can square both sides. Distributor FOIL out on the left-hand side. Right-hand side, squaring negative 49.2 is 2420.64, and the root goes away from the n. Bring everything to one side. We get it in the quadratic, get it set up for the quadratic formula, divide it out by 10,000. You can do the quadratic formula on this. And you get two answers here. You get 22.3, 17.9. Now, you have to really check back in the original here. And in the original situation, we do have a negative sign in this on the right-hand side. And so the 17.9 does not work. It's going to be 22.3. We need a whole number here, so we have to round up to 23. So we need to be 95% certain that this will run for at least 2,000 hours. The threshold we need is at least 23 of these components. All right, this concludes lesson 24 on the central limit theorem. As always, if you have any questions, comments, please don't hesitate to email. Thank you.